I guess I'll just quickly go over this problem on the recording. But for the very first problem on the practice midterm, it was essentially asking you to start with this function right here, this slightly nasty fraction. And the idea is that you had to match it up to one of the definitions of a limit. And there's the version with the h, and there's the version without the h. And just by inspection, it looks almost exactly like the version without the h. The idea here is that you basically match up the terms, so you can kind of see that 3 is a. And what happens here is if this is f of x, it lines up with 1 over x plus 1, which is how we basically gleaned that the original function is 1 over x plus 1. And just as a sanity check, we notice that if we plug in f of a for a is equal to 3, right? If we plug in f of 3, this just becomes 1/4, which matches up nicely with what's over here. So yeah, that's the first part of the problem, where we figure out that f of x is 1 over x plus 1. And then in actually taking the limits, which is the second part of what the problem asks, right? The limits of this fraction right here, the way to usually go about this is to start by putting things over a common denominator. So multiply this term by 4 over 4, and this term by x plus 1 over x plus 1, which is exactly what I've done here and here. And then at this point, everything's over a common denominator, and you can just subtract. And you see that you're going to get 3 minus x, which is going to cancel out nicely with this thing down here, and leave you with a -1. You plug in x as it approaches 3 at the very end, and you should end up with -1/16. And this matches up nicely from the power rule, which I just did as a sanity check. If I was a student and I was familiar with power rules at this point, even if the problem asks you to calculate the limit, I think it's helpful at the end to just quickly do a power rule check to make sure you've gotten the right answer. Of course, the teacher's probably going to make the points for the problem come from actually doing the limit. I'm just advising as a sanity check to go through and do it with a power rule. So what is this? This basically x plus 1 to the -1 essentially, and you bump it down, square it, and it becomes -1 over 16th. So I think that's probably correct. Okay, ready to move on? Or any other questions about that one? Gotcha. I think one of the students was asking me in particular about showing that there was a root of the equation cosine pi root x is equal to e to the x minus 2. Would you like to do that first, or do you want to just go in order? I haven't actually looked at...
actually.
What's up?
Can we do that one, actually?
Yeah, okay. We can quickly skip ahead. I think that's problem 4, and we'll come back to any of the ones that we want to take a look at. But since a student asked me about that one in particular, and I think it's one of the trickier ones if you don't know exactly what the strategy here is. But the question is asking to show that cosine pi root x equals e to the x minus 2 has a root in the interval 0 to 1. And just as a brief reminder, to say that it has a root in this interval means that there's some value of x between 0 and 1 that satisfies this equation, that makes this equality true. Yeah? So when you have a problem with really, really nasty functions like this, like cosine pi root x, I don't have a great way of visualizing that, really. And e to the x is, well, also hard to visualize if it's combined with other stuff. If you have a nasty continuous functions, and you're asked to prove that a root exists, does anybody know the trick to these kinds of problems? There should be one technique in particular that this kind of problem is screaming for you to use.
It's the either the IVT?
Exactly, intermediate value theorem. For this kind of problem where cosine pi root x is continuous in the interval, e to the x is continuous in the interval, and the constant function 2 is also continuous in the interval, everything's continuous. So what we want to do is we want to use intermediate value theorem, which only applies to, I believe, continuous functions, right?
Yeah.
To try to prove that a solution exists. The reason why I say it's screaming is because this solution is so complicated that we're not going to be able to find the exact solution by hand. but questions where you're asked to prove the existence of a root, prove the existence of a root should be screaming IVT.
Mm-hmm.
So the strategy for these problems is just to define a function, let's maybe call it f of x, is equal to basically this entire thing just moved to the left-hand side. Minus e to the x plus 2. And we're basically looking for roots where, so basically, show there exists, this is a symbol for there exists, in A, such that f of A is equal to 0. That's what this problem is asking us to do. Yeah? And so let me ask you this. What's your comfort level with intermediate value theorem? Like, do you understand it deeply? Or do you feel like it's just sort of a bunch of, a theorem where they just say a bunch of things and it gives some results, but you're not really sure what's going on? Like, can you visualize intermediate value theorem?
Yeah, so basically it states on a given interval, it's assuming it's continuous, right?
Yes.
That because, well, the way I understand it at least is that you plug in the left hand limit and the right hand limit, or
Sure.
the interval.
Okay.
And as long as those two boundaries contain a root between them, then you could prove that there is a root, at least one, at least.
Yeah, that's the idea. So like the suggestion goes, let's just plug in 0 and 1. I know that the interval here is not inclusive of 0 and 1, but for the purposes of intermediate value theorem, it's fine if we use the endpoints. So f of 1 is equal to cosine of pi minus e to the 1 plus 2. So what does the first one come out to? This basically becomes 1 minus 1 plus 2. So this is a positive number. Yes?
Yeah.
And this one down here is negative 1 minus 1, or sorry, minus e plus 2. I don't know what that is exactly, but that looks kind of like negative 1.7 or so. I don't really care about the specifics. So what this is saying is basically, if you plot out the number line of x versus f of x, the way to visualize intermediate value theorem, and I'm just sort of putting into picture what our friend here was saying, was that at x is equal to 0 and x is equal to 1, the idea is that the value of f of 0 is positive 2, and the value of f at 1 is somewhere around negative 1.7. But the fact that this is positive up here and this is negative down here means that if I was to draw a continuous line, and remember it's a continuous function, so it kind of corresponds to a continuous line, like if I have to be positive on the left side and negative on the right side, like I have to cross 0 at some point, right? The intermediate value theorem is just saying in a mathematically rigorous way what is, I think, really, really common intuition, that if I'm starting up here and ending down here, yeah, I've got to cross 0 because my pen is not allowed to teleport because it's a continuous function. Does that intuition make sense?
Yeah, that makes a lot more sense.
Yeah. So like intermediate value theorem, sometimes when you're reading theorems, it can be really, really hard to decipher what they're saying. But at least for intermediate value theorem and a lot of the stuff that you see at the intro calc level, there's really, really good visualizations or intuitions like this that should make what's actually happening in the problem really clear. So this is the visualization. What would you actually put for an answer? I would probably say, by intermediate value theorem, or rather I would say, we know that f of x is continuous. We know f of 0 is greater than 0, and f of 1 is less than 0. So by IVT, there must exist a value, let's call it a, such that f of a is equal to 0. And the fact that f of a equals 0 means that, so a, or rather x equals a, is a solution to original equation. So if you just circled and boxed this answer is probably going to get you full credit right here. in addition to the little calculation over here. Does that make sense?
Yeah,
I think someone in particular was asking us about this question, so I hope that clarifies it.
Yeah, that was me, and it helped a lot. Thank you.
Very good, yes. But I think the big takeaway here, I'm just going to stress, for any situation where you have kind of terrible looking continuous functions and you're asked to prove that a root exists, but not necessarily to find it, it screams intermediate value theorem. Should be the very, very first thing. And just to put it into a more useful form, define an f of x such that you sort of put everything to one side. And then you're just searching for when f of x or f of a is equal to 0. Yeah, anything else to say about that problem? I think that should cover it pretty good. I guess the last thing to stress about intermediate value theorem is that if you're actually being asked to find at what point it crosses 0, or if you're actually being asked to find what the root is, intermediate value theorem is honestly not so helpful in those cases. It's good at proving existence, but not good at proving, not good at actually finding or calculating the points of interest. Yeah.
Mm.
Oh, and by the way, the function could also be doing something totally crazy, like looping up and down a couple of times. But so long as you can guarantee that it's positive on one side and negative on the other, you're guaranteed at least once crossing 0. And if the problem was worded slightly differently, or the function was slightly different, to where the function was negative over here and positive over here, it's really no different. The same idea holds that if it's positive on one side and negative on the other, it's got to be crossing. So I want you to think sort of on your feet and not necessarily get pigeonholed into exactly the problem that I solved, but I hope that you can sort of take these ideas and apply it to whatever you see in your midterm. Sound good so far?
Yeah. In situations where you have a positive on both ends of the interval, would it still apply, or is it just negative and positive? Or
if we're a situation where there's a positive value on both ends, is there any guarantee that I cross 0?
I wouldn't say so, no.
Yeah, I also agree. But this is a really, really good question, because there's a slight chance that the professor doesn't give you quite as nice of a... Like, the fact that they gave you 0 and 1 right here were almost dead giveaways, because it worked out so nicely that one was positive and one was negative. There might... Now, this might be kind of nasty to put on a midterm, but it's possible. It's possible that the professor might have given you maybe a bigger range off the top of off the start. Like maybe they said from 0 to like 10 or something. And maybe it's not very clear. Sorry, what am I trying to say here? Maybe it's not very clear what the intervals ought to be. In a situation like this, you probably might need to test a couple of points to try to get a feel for a pair that you can make positive and negative. You see what I'm saying? Like if they gave you a slightly different problem with an interval where the endpoints are positive and positive, you still might be able to use intermediate value theorem if you dig around a little bit, and if you're able to find for yourself whether there's a point in between that's negative. You see what I'm saying?
Yeah, okay, I get you.
It's like if the endpoints, don't immediately satisfy intermediate value theorem, like don't give up right away. Check to see if there are maybe some nice points in between that work too. Yeah. Okay, on to the next problem. Someone also asked me about finding a horizontal and vertical asymptote question. I guess I can do that one next, unless anyone has any other suggestions. So I believe this one was question 7. So I think the question was just asking x squared minus x minus 6 and x squared minus 2x minus 3. And for questions like these, you always try to factor these out first and try to see if there's any cancellation that you can get. So I believe this is x minus 3 and x plus 2 over x minus 3 and x plus 1. Is that right? Yeah. So the x minus 3's cancel out, and this basically just becomes x plus 2 over x plus 1, just with a single point discontinuity at x is equal to 3. POD means point of discontinuity. So if this is more or less the behavior of the function, at this point we just look at, we can basically just look at the denominator to figure out what the vertical asymptotes are. And we can look at, we have to look at both the numerator and denominator to figure out what the horizontal ones are. So you can really do whichever one you want. So I'm just going to draw out the graph here. But at a glance, it seems like at -1, x is equal to -1, it looks like this is blowing up. Because, you know, as x approaches -1 from the left or from the right, it looks like this is approaching infinity or negative infinity. So that's the vertical asymptote. As for horizontal asymptotes, it looks like as x approaches infinity, it looks like the limit is just 1. So I'm going to draw that out sort of like that to indicate that this height is sort of a positive 1. And also when x approaches negative infinity, well, same deal, right? It looks like it still approaches positive 1. So I believe the horizontal asymptote is just going to be 1, and the vertical asymptote is going to be -1. And they don't explicitly ask you to graph this, but if they did, or just for the sake of a sanity check, it looks to me like this graph would look something like, well, as it approaches -1, we sort of have a sign change, right? Yeah, as it approaches -1, we sort of have this behavior where it looks like it's going to approach negative infinity coming in from the left. Because, you know, if x is equal to like -1.1, the top term is going to be positive and the bottom term is going to be negative. So it looks like it's approaching negative infinity. Whereas coming from the other side, it looks like it's approaching positive infinity. Because for x is equal to, let's say, -0.9, well, this is going to be positive and that's going to be positive. And yeah, that's basically how you do one of these problems. Sound good?
When I did this one, I put x equals 3 as an asymptote as well, so that wouldn't be an asymptote because the x minus 3 cancels out on the top and the bottom.
Yeah, exactly. So the issue with x minus 3 is that the point is undefined. I kind of glossed that over when I graphed it. It is indeed undefined because if you literally try to plug in 3 here, like the denominator of 0 is just nothing you can do. But because it sort of cancels out, you're not actually going to have it blow up or anything like that. It's the limit from the left and the limit from the right are going to agree nicely with each other. So
Okay,
it's
I
not an
get that.
asymptote.
Thank you.
Sure. Very reasonable question. I'm happy you brought it up.
For the horizontal asymptote, you would want to find the limit of the function as it approaches infinity, right?
Yeah. Just I think for horizontal asymptotes, you basically just look at positive and negative infinity. Are there any exceptions? Is it possible to have a third? Sorry, is it possible to have a horizontal asymptote anywhere else? I don't think so, right? I don't think so. Okay, so as a rule of thumb, I think there can be any number of vertical asymptotes, right? It could be 0, 1, 2, 3, infinity. But I think there can only be less than or equal to 2 horizontal asymptotes, right? Can anyone find an exception to this? It's been a while since I've thought about this, but I think you can get one asymptote going in negative infinity and potentially another asymptote going to positive infinity. So I think you can only have at most 2 horizontal asymptotes, right? Am I making sense here? Yeah.
Oh, okay. I think so because you could really only approach negative infinity and positive infinity. You're just
Yeah, you can only
at
have,
least it seems like it's limited to 2.
right. Like if they approach different limits, that's 2 horizontal asymptotes. But for this problem, they approach the same value 1. so there's only one horizontal asymptote. And, well, I guess it's also possible that there are 0 horizontal asymptotes if the domain is just cut off. But that's kind of an edge case. So far, so good?
Yeah, can you explain a bit more on how you got the horizontal asymptote for that question?
Yeah, sure. So basically, what I did was, once I had x plus 2 over x plus 1, I basically just looked at the behavior as it went out to positive and negative infinity. So positive infinity, just limit as x goes to infinity of x plus 2 over x plus 1. Well, it's pretty clear that this limit is just equal to 1, right?
Yeah.
So that's one asymptote right there. If you want to think about it a little bit more closely, this is saying that as x gets humongous, the numerator and denominator are still slightly different numbers. So it's never exactly 1, but at a certain point, once x gets humongous, the 2 and the 1, really don't make a big difference anymore. So the thing gets arbitrarily close to 1. That's how I would reason about the positive infinity. Negative infinity is almost identical. So x plus 2 over x plus 1. In this case, because, again, the 2 and the 1 don't make a huge contribution, as it goes to negative infinity, this thing just sort of looks like negative infinity over negative infinity, which is just 1.
Okay.
That's kind of a
Sorry,
sloppy way of thinking about. What's up?
I was looking at the vertical asymptote and I was confusing myself. I confused it with the horizontal.
Oh, so you were actually confused about the vertical asymptote?
No, not really. It's just that
Okay.
when I was looking at -1 of the vertical asymptote and confused that, or I mistaked it as the horizontal asymptote, and I realized what I was looking at.
Gotcha. Yeah, sorry. As I mark this thing up, my handwriting starts to get a little bit messier. But I think for the bottom line for this question, the horizontal asymptote is going to be 1, and the vertical asymptote is going to be at -1. And I think that constitutes a complete answer to the problem. Okay. Any further suggestions? Someone was asking about what is this? Number 19 for section 2.7. Feel free to share any homework problems with me. I just don't know what the problem is.
Which one was it?
This is someone saying in the general chat.
Oh, okay.
Number 19 for 2.7. I'm happy to take a look. I just don't know what the problem is.
I'm trying to look for it. So I believe 19 is asking for the derivative. Well, the derivative of a at the given number a, and the equation would be f of x is equal to square root of 4x plus 1.
Square root of 4x plus
Plus
1.
1. Yeah, and a equals 6.
And a is equal to 6. I'm sorry, are we trying to do this with limits, or are we trying to do this with power rules?
It's, I believe it's asking for it in the limit definition of f of a plus h.
What a pain in the butt. Okay. I mean, I'll take a crack at it. I don't know this off the top of my head, and I'm very rusty, but maybe I can figure it out. So I usually prefer using the h's rather than not using h. And I think this just turns into x plus h minus fx over h, right?
Yeah.
So the limit as h goes to 0. Is that right?
Yeah.
Okie dokie. And I guess you just plug in a is equal to 6 here and here. Okay, I'll take a crack at it. No promises. But to me, this looks like the square root of 4 of x plus h plus 1 minus square root of 4x plus 1 all over h. Is this it? Is this it? This
Yeah,
looks
that
kind of
should
terrible,
be.
but we're gonna multiply by the conjugate and just cross our fingers and hope something nice works out. Okay? Limit as h goes to 0. So multiplying top and bottom by the conjugate, and stop me if you have any better ideas, because I really don't like these kinds of problems. I haven't done them in a long time. But hopefully something nice works out. So 4 of x plus h plus 1 plus root 4x plus 1. So we're just multiplying top and bottom by 1. Or sorry, we're just multiplying this entire thing by 1 so it doesn't change, right? And this becomes 4 of x plus h plus 1 minus 4x plus 1. Remember that the cross terms go away because this is a plus and this is a minus, right? It's a difference between squares.
Yeah.
And then the bottom becomes h and 4x plus h plus 1 plus 4x plus 1. Okay. Yeah, looks like we're going to get some pretty nice cancellation, right? Because all that's left in the top is going to be 4h, if I'm not mistaken. Right, 4x and 4x cancel out.
Yeah, and so is the negative 1.
Yeah, 1 and minus 1. So all we're left with is 4h there, which cancels out with the h over here. And then we're just left with some radicals in the bottom that we're just going to hope behave nicely. Hope. So remember, every single one of these has a limit of h goes to 0. I've just been a little bit lazy, okay? If you're being graded on this on a test, probably write them out. But this looks like limit as h goes to 0 of 4 over the radical terms. X plus h plus 1 plus 4x plus 1. And, well, what does this look like? I think at this point we can just maybe go ahead and just sort of plug in 0 for h, right?
Yeah.
So that's sort of 0, and at this point they just kind of turn into the same thing. So hopefully this is just 4 of 2, 4x plus 1. Does that seem right? Square root of 4x plus 1. My own handwriting is terrible. And then you just plug in, was it
6,
a is equal
right?
to 6?
Yeah.
Yeah, so then for a is equal to 6, this becomes... looks like a 0. It should be a 6. So that's 4 over 2, 25?
Yeah.
So that becomes 4, 2 times 5. Does that seem right? So it becomes just 2/5?
Yeah. Yeah, it should be correct.
Okay. Hopefully that's the right answer. As a quick sanity check, like always, what's up?
Yeah, that is the answer.
Oh, very good. As always, I like to do sanity checks for these because once you do know the power rules, right? F prime of x is equal to... Oh, wait, so f of x is equal to 4 over rad 4x plus 1. I'm sorry, why did I write that in the bottom? It was just 4... Was it just this? Was the original function?
Yeah, that was just the original.
So then, to do the power rules, you just sort of bump the 1/2 out in front, and this becomes a 4x plus 1 to the minus 1/2, and then the chain rule, you get an extra 4. So this turns into 2 over 4x plus 1. Yeah, and I think that agrees with exactly what I had over here. So very good. By the way, have you all learned the product rule and division rules at this point?
For derivatives?
Yeah.
No, right now, the most he's gone to is just getting the derivative using the definition of derivatives.
Okay, gotcha. That's fine. So it looks like you've basically just been introduced to the power rule using the definition of limit, right?
I'm not sure, to be honest. I think
Okay.
he may have mentioned it in the video.
All right. Wait, so have you actually learned the power rule, or are you still strictly on limits?
Well, for the current class, I don't think he's taught it yet.
Okay.
It's just that I just know it from high school.
Okay, gotcha. So if he hasn't actually taught you how to do the limit using the power rule, because using the idea is doing the rigorous arguments with the limits sort of provides justification for all the rules that you'll use in the future, like power rule or a product rule or a division rule. I think I was misled a little bit, where I sort of assumed that all of you had seen a bit of the power rules at this point. But if this doesn't make sense to you, then ignore it. You're going to learn this sometime soon. But if you have seen it before, you can use it as a sanity check to make sure that you've done your limits correctly. Okay? If you don't know what this is, then just make sure to do your limits correctly, because you don't know how to double check it yet. All right. Any other problems? What else would you like me to take a look at?
I have a problem, if that's okay.
Yep, let's go for it. What's up?
Okay. is it okay if I send a screenshot of it in the Discord chat?
That's perfectly fine. Just put it in general, I guess.
Yeah.
By the way, if you want to review any of this, I will put this up on YouTube afterwards to serve as a reference. And for anyone that couldn't make it, they can hopefully get in on it in retrospect as well. But okay, so the new question is x squared minus x minus 6 over x. And okay, they're calling the function m. Okay, very first thing to do, as always, is to sort of split it up and see if there's any cancellation. I believe this time there will not be. But x minus 3 times x plus 2 over x. So this time, it looks like the only thing in the denominator is x. So we're going to expect a vertical asymptote. We're going to expect a vertical asymptote at x is equal to 0. Right? So I'm going to draw it just on the side so you can see it. But x is equal to 0, probably going to be an asymptote. But other than that, let's just look at the limiting behavior, right? It looks to me like the limit as x goes to infinity for the horizontal asymptotes is basically going to be right. So as x squared minus x minus 6 becomes extremely large, it looks like this term is just going to dominate, right?
Yeah.
I guess the very careful way to do it is divide everything through by the leading term, divide by x squared. But a little bit less formally and just sort of more intuitively, x squared is going to out-dominate everything over here, and it's also going to dominate over this x, right? Because basically what I'm saying is you can kind of ignore these for now and just say this is kind of looks like x squared over x, which is just basically x in the limit. So then as x goes to infinity, well, just the term x by itself goes off to, well, infinity. So we would say that, I wouldn't really call this a horizontal asymptote, right? I don't think you call this sorry, this is basically just a definition thing. In your class, do you consider something going off to infinity to be an asymptote at all?
I don't think so. I've had a question like that too, but I haven't asked the professor.
Yeah. I personally would not call this a horizontal or a vertical asymptote. I'm talking specifically about the behavior going off to positive infinity. We can take a quick look at negative infinity, but what's that going to look like? The idea is still going to be very similar, x squared minus x minus 6 over x. Again, it's going to be x squared is going to dominate the top, so you can kind of just ignore these. And at this point, you're just sort of comparing x squared to x. Sorry, I should have drawn it as negative infinity. So this just turns into, again, just x, right? So this goes to negative infinity. So that looks something like blows up down there. Does that seem right? I can quickly graph this on Desmos too, just as a sanity check, but I'm assuming that none of you are going to have Desmos on a test.
No, I believe it's no calculators.
No calculators? Ooh, that sucks.
Yeah.
There was actually one question in the study guide that is a little bit tricky. Yeah, okay, I got this right. So just graphing it on Desmos, it's kind of a pain to share my laptop screen, but this looks kind of like it changes inflection up there, and it basically looks like that. Yeah. But if the question is just asking you to find the vertical and horizontal asymptotes, I think I would just tell them that the only asymptote here is the vertical one at x is equal to 0. Seem reasonable?
When you would plug in negative infinity to the x squared, the negative sign stays?
Because it's sort of like, yeah, I guess it's sort of like negative infinity squared over negative infinity. So like the positive,
Oh,
okay. The top is going to be positive and the bottom is going to be negative, so there's overall going to be a negative.
Okay,
yeah.
Then.
Yeah. Sometimes the arguments of the negative sign can be really subtle, especially if square roots are involved. Like I think there was that one problem where, because it was approaching negative infinity, do you remember that problem? It was kind of like
square root of x squared.
Yeah, plus like, I don't know, was it like 7x? Plus, sure. I think 6x over. No, what was the problem? I actually think I did make a video about this one, because so many people were asking about the exact same thing. Let me see if I can quickly find it. Yeah, do you remember? Yeah, conjugate radicals, exactly. It was this problem. So at the limit as x goes to negative infinity. I'll just quickly go over this one, because I think this was probably one of the harder ones. But the issue here was that if you multiply top and bottom by a radical, which is the right approach, you're still not really done, because you still require some careful arguments about the signs. But once you do this, this becomes 36x squared plus 7x minus 36x squared. So those two cancel out. But there's still kind of this nasty radical down below. Yeah. And the idea here is that limit as x goes to minus infinity.
You would want the negative sign on the...
Yeah, you got to be really, really careful about your signs here. Because how do you like to argue about it? You can think about dividing through by x, or what I like to do was I sort of like to think about pulling this x squared out, so that this turns into like root x squared 36 plus 7 over x minus 6x on the bottom. But the issue is that because this is the square root of x squared as x approaches negative infinity, well, this term right here is positive, right? So this is basically absolute value of x, because it's the positive square root. But because x itself is negative, this is basically equal to negative x.
Mm-hmm.
So when you rewrite this basically becomes 7x over negative x, 36 plus 7 over x minus 6x. And at this point, you can cancel out all the x's. And I think this ends up getting you 7 over like negative 12 or something like that. But this negative sign is really important, because if you forgot about that like careful argument and didn't have this negative sign, then this would just become sort of, oh, and remember the 7 over x just sort of goes away because the limit is x goes to negative infinity, so and this one just disappears, right? But the issue is that, if you didn't remember to do that negative sign, then this becomes, if you didn't remember that negative sign, then this becomes like 6 minus 6, which is indeterminate, right? Or it looks like it blows up.
Yeah.
But that negative sign is really essential to this problem.
And you could also do the one where you divide all the terms by its leading.
Yeah, you could also think about it that way, right? So like you could sort of think about, just going to rewrite it like this. So that's another way to think about it, and maybe that's the cleaner way. But if this is 36x squared plus 7x minus 6x, right, you can think about dividing everything through by x, divide this by x, and divide this by x, right? Mm-hmm. And then I think the subtle argument goes that when you're moving this x inside the radical, Remember, this x is a negative number,
Yeah.
right? So you can't just and the argument of a radical has to be positive. So it's kind of like
You could factor out the negative one,
exactly.
right?
It's almost like you're moving the absolute value of x inside and leaving the negative outside. So then this becomes 30. So then you're dividing 36x squared over x squared plus 7x over x squared, and there's a negative sign out front, minus 6. And then this leads you to the exact same logic as we had up here.
Okay.
But, yeah, they're ultimately equivalent, but this problem was tricky. It took me a little while to figure out what the heck was going on because I kept running into that denominator blowing up. But,
okay.
Yeah, be very, very careful about your signs if you're approaching a negative value or negative infinity.
And this just usually applies when you're approaching negative infinity and your x value happens to be a radical x squared.
Yeah, I mean, I think the exact same problem would occur if it was just any negative value, right?
Okay.
The fact that it's infinity is only relevant for getting the 7 to disappear. But other than that, I think the subtlety with the signs has to apply for any similar problem. Let's say this was approaching negative like 10 or something.
Okay.
Yeah. Someone was asking about a problem we just did a little bit earlier with cosine pi root x equals e to the x minus 2. We actually covered that a little bit earlier, and I'll post a recording of this video up in case you want to access it. But if in the meantime, if you want a hint for it, you can try out using intermediate value theorem. And hopefully that makes some progress. Yeah. Any other new questions at the moment?
Why did you cross out the negative 6x, like 3 lines up?
Why did I cross out the negative 6x?
Yeah. On the far right.
On the far right? I was just crossing out the x to indicate that because there was an x here, there was an x here, and there was an x here, and I just divided through by x, top and bottom.
Okay.
Gotcha. Yeah, it's to write this in just a tiny bit more detail. Then the next step would be 7 over 36 plus, I think it was like 7 over x minus 6. And that's the limit as x goes to negative infinity. Negative infinity. Yes. More questions, folks? What else is confusing? Did you want to look at some of those piecewise problems? What's up?
Yeah.
Yeah. So, okie dokie. I'm looking at question, I think 3D in particular. Actually, you know what? Let's just work through all of question 3, if we so please, from the study guide or practice midterm. So it's asking find discontinuous values. So discontinuous, if any. And no work needs to be shown, which is great because I'm lazy. But if this is x minus 5 and x minus 5, x minus 2. So one thing to watch out for is like, yes, but like you can cross these two out sort of and just realize that the function more or less looks like x minus 2, but you can't forget about x being equal to 5 as a point of discontinuity, POD. Like what it looks like is, so if you graph out 1 over x minus 2, right, okay, there's going to be a vertical asymptote at x is equal to 2 as well. So it's going to look something like this, right? This is 1 over x minus 2, but because there's a pointwise discontinuity or just a point discontinuity at 5, it's going to look like there's going to be just a single gap right there. So those are your 2 points of discontinuity, basically this one and this one. Yeah?
Yeah, so why exactly wouldn't it be another vertical asymptote?
Because the idea is that x minus 5 and x minus 5 sort of... Okay, if I covered up this sorry, let me put it this way. If I got rid of this and it was just a 1 up top, then yes, this would blow up. But the idea is that because it's an x minus 5 up top, as it approaches as this function approaches positive 5, this thing right here and this thing right here, their behavior totally mirrors each other. So this thing up here kind of like prevents the bottom one from blowing up, right? To just give you a very simple example of this, let's say g of x is equal to x over x, right? And we all know what this function ought to look like. This is just x over x is basically just 1, right? And the idea is that as it approaches 0, if you get arbitrarily close but don't touch it, the value of this function, the height of this, is still going to be 1. But just at 0 itself, it's undefined because you can't have a 0 in the bottom. But like, I'm hoping that this analogy makes it clear why it doesn't really blow up. It's not a vertical asymptote at x is equal to 5 up here. It's just a point of discontinuity.
Okay.
Yeah. Like if this doesn't blow up, which it doesn't, then this also should not blow up. You see?
Yeah. Okay.
Yeah. Okie dokie. Okay, and the next one I think is f of x is equal to 1 over root x minus 4. I'm pretty sure it's just going to be at 16, right? Because root of 16 is equal to 4, and that's when it is going to blow up. I should note that I'm pretty sure this is the only one, because you can't have the square root of negative 16. Let me put this. So this is 16. I think this ought to just look something like this, yeah? With a vertical asymptote like that. So 16, I think, is your only point of discontinuity here, unless I'm sorely mistaken.
I think that should be the correct answer.
Okie dokie. And for the next one, f of x is equal to 1 over cosine of x minus 1. Well, this is going to blow up whenever the denominator is equal to 0. Right? So whenever cosine of x is equal to 1, it blows up. And when is at this point, we just have to answer, when is cosine of x equal to 1? Well, if we graph cosine, it happens at every single peak, right? Every single peak. And I think this is what, 2 pi, and this is 4 pi, right? So it hits that peak. So this is cosine of x, and this is x. So this basically blows up for whenever x is equal to some multiple of 2 pi. Which is another way of saying that there's infinite points of discontinuity in this problem. Does that make sense?
Oh yeah, because the when it's a cycle, right?
Yeah, exactly. So this is the graph of cosine of x. If you were to actually graph out this function, I think it would look something like this, maybe? I think it's going to look a lot like tan of x, to be honest. Because it blows up for the same reason.
So this is kind of a stupid question, but what do you mean by blows up? Because I'm trying to follow along and
Oh, gotcha. Well, thank you for asking, because blows up is sort of colloquial language that gets used all the time in math or physics. But blows up means just goes to infinity. Just the number gets absurdly huge. That's what it means.
Okay.
Right?
Thank you.
Yeah. Okay. Thank you so much for asking, because there's probably other people with the same question. And I'm sorry I didn't clarify that. I guess I've just been using the word blows up for so many years that it's just become second nature, right? It's just, if mathematicians, if you don't want to feel fancy, use the word blow up. If you want to feel fancy, you start talking about epsilons, deltas. But the idea is that, just to use it in the language of this problem, every single time x takes on a value of a multiple of 2 pi, so whenever x is equal to k 2 pi for some integer k, well then cosine of x minus 1 becomes 0. So then the 1 over the denominator becomes huge as you get close to that point. Yeah.
I have a question on the one you did before this.
Sure. What's up?
Would it also be discontinuous everywhere where x is less than 0 since there's a square root?
Okay, so that's a very reasonable question. And I think at this point it sort of turns into a matter of semantics, right? Like the function is just straight up undefined to the left of, for x is less than 0. The function is just sort of straight up undefined. It's not even on that domain, right?
Yeah.
So this is sort of a, more semantics question than math. It's like, if it's not even exist there, is it discontinuous? Right? It's like, if a tree falls in a forest, except for there is no forest, does it make a sound?
Okay, thank you.
Yeah, I would, if you made it clear what you were talking about, I would hope that your professor doesn't take points off. But my natural interpretation of the problem is that would be that you would only talk about it for x greater than or equal to 0.
Okay.
Yeah, I think it's a very reasonable question, though. And thank you for bringing it up. Okay, so now we're on... What's up?
Quick question. You said this was going to be uploaded to your channel, right?
Yeah.
Okay, sounds good.
Yeah. No, I usually just link it to, if there's a resource or whatever channel in the Discord, I usually just upload it and put a link there. But I'm just a hobbyist. I'm not part of this class, but I help out with a couple of math classes here and there from the UCals, and basically just every week or so do a homework or review session, depending on whether there's a homework or test coming up. And I'm happy to do like one of these every week for, a couple days whenever homework is due. Anyways, f of x is equal to, the next one is x squared, tangent of x, and 3x, right? So this is for x is less than or equal to 0, for 0 less than x less than or equal to 2, and if x is greater than 2. And for this problem, you just sort of have to graph it a little bit to see what's going on. So for the first part, for x being less than or equal to 0, it looks like a parabola. And then for tan x being, between 0 and 2, this behavior is... It's kind of funny. First of all, we're kind of need to assume that tan is working in radians. I think it's typically assumed that it's working in radians unless degrees are specified. But if I remember correctly, tan kind of looks like, right? So tan is just, tan of x is sine over cosine, right? So if you remember, it kind of looks like, tan of x kind of looks like a bunch of these with a bunch of asymptotes, right? Yeah. And one of the questions we got to ask ourselves is, does the first asymptote happen within the bounds of this, within the bounds of our function here? Within the bounds of this 0 to 2 where the tan behavior is being defined. And to just remind ourselves when that happens, that's whenever cosine is equal to 0. So I'm going to use the term again, blows up whenever cosine of x is equal to 0. So that's x is equal to pi over 2, 3 pi over 2, etc. etc. And as it so happens, pi over 2 is indeed within the bounds of 0 to 2. Right? So what this is going to look like is, it is indeed going to blow up to an asymptote. My pen is a little bit frozen right now. Sorry, hang on. Are you all still there? I think my computer froze.
Yeah, we're still here if you can hear us.
Just give me a second to restart this. Okay, we're good. For whatever reason, my pen freezes up now and then. But so this point right here is pi over 2, which is about 1.6, right? 1.57. And then tangent sort of starts picking up again until it reaches x is equal to 2, at which point the behavior 3x takes over. So 3x is just going to look like a vertical line. Right? So, and this height in particular is going to be 6, because 3x takes over when x is greater than 2. So it just sort of starts right when x is equal to 6. So for this problem, I would say there are two discontinuities. This asymptote and this jump discontinuity. And you notice that I'm sort of glossing over the details here a little bit. But, you know, how do I put it? The tangent of 2 is equal to sine of 2 over cosine of 2. And if you remember the unit circles, sine is positive up here and up here, negative down here and down here, whereas cosine is positive here. So this is sine. Cosine is positive over here and negative over here. So if I'm not mistaken, at an angle of 2 radians, you're going to be somewhere in this regime, quadrant 2. So cosine is going to be negative. So cosine of 2 is negative, and sine of 2 is positive. So tangent overall is negative. Right? So tangent overall should be somewhere down here in the, below the x-axis, whereas the next line, 3x, picks up above the x-axis. And that's why I'm sure that there's a point of discontinuity here. Right? I think you basically have to do a check like this. Otherwise, for all you know, maybe tangent of x just happens to perfectly leave off where the next function picks up. You see what I mean? This question, I think, is one of the trickier ones on the homeworks on the review session. But do you understand my point? Because we check the line, we know that it doesn't cross the line. Or rather, we know that at x is equal to 2, tangent is still somewhere down here, whereas y is equal to 3x is up here. So there's no way that these two touch because one's negative and one's positive.
Can you explain how you know that sine 2 is positive and cos 2 is negative? Okay.
Yeah, of course. That's just remembering my trig rules. So if this is pi over 2, which, let me draw it bigger, okay? So pi over 2 is about equal to 1.57, right? And pi is equal to 3.14. That means that a value of x is equal to 2 is going to be somewhere, 2 radians is going to be somewhere in this quadrant. You see that? And just from memory, we know that in this quadrant, sine is positive, but cosine is negative. Does that make sense?
Yes, thank you.
Yeah. This question, I think, is probably the most involved one I've seen on this exam. I think it takes a lot of tracking things down to their logical conclusion in order to fully justify why there's 2 points of discontinuity. Do you all think you would have gotten this problem on the exam? What's the comfort level in the room right now?
I feel like a 60.
A
or
60?
Yeah.
50%. Yeah.
Okay.
Like 60, 70.
It's not too bad. It's not too bad, I guess. All right.
For the overall midterm or for just this question?
Either or. For this question in particular, I think there was quite a bit of subtlety to this one. And I would expect that this is one of the hardest questions on the test.
So our point of where just it isn't continuous anymore. It'd be pi over 2 because that's when it starts approaching positive infinity, and it really never crosses that line.
So there's 2 points of discontinuity, right? So there's two. I guess there's 2 discontinuities. One is an asymptote, and the other one's a jump discontinuity.
Oh, okay.
Yeah. Fun little problem. Okay. I guess if there's no more questions on that, I guess I'll tackle the last question about discontinuities. I think it's part E. But f of x is equal to x plus 4 if x is less than 2, 6 if it's equal to 2, and 1 over x squared if x is greater than 2. So I guess my general advice to these is always to just sort of graph them out the best you can and see if you can get them to look somewhat reasonable. But if the y-intercept is 4 and it's going up, right? So as it approaches 2, x plus 4 is approaching 6, which matches up perfectly with this next point. So at least coming from the left, there are no issues, there are no discontinuities. Yeah? But then on the other side, it's like saying 1 over x squared, and the limit as 1 over x squared approaches 2 from the right is 1 over 4. So 1/4 is somewhere down here, and what that's saying is, I guess it's doing something like this. This problem is a little bit weird coming from the tangent problem, because that one was very subtle, and I feel like this one in comparison is a sledgehammer. But to me, it seems like there's just one big jump right here, and that's it. I don't think there's anything else to say about it, is there? Any questions about any of these? Alrighty. What other questions do you want to tackle?
Would you actually mind doing this one in here? I replied to the attachment in office hours if you can do that problem. I didn't really understand when the professor did that at first.
Sure. So what are you being asked? Find the equation of the tangent plane to the curve at some point?
Yeah.
Okay.
Y equals 3 over x plus 2 at 0.11.
Sure, okay, that seems reasonable. Y over 3x plus 2 at 0.1 comma 1. Yeah, I hope to, oh my goodness, she wants to do it with limits? Okay. Alright. Damn, that sucks. So let me start with a high-level overview of what this problem is. So we're trying to look for the tangent line to this function at 0.1 comma 1. So high-level breakdown of what this is. So this is sort of your first introduction to finding tangent lines, and I think it might come off as a bit overwhelming, but the calculus portion of this, so this problem gets broken down into a calculus part and non-calculus part, yeah? And the calculus part does one and only one thing. It lets you find the slope at 1 comma 1 because the derivative is equal to the slope. Exact same thing. The derivative is equal to the slope. So derivative of function is equal to slope of tangent. So that's the calculus part of the problem. And then the non-calculus part is literally 8th or 9th grade math. The non-calculus part is given the slope at this point and point 1 comma 1, find equation of line. Like literally y is equal to mx plus b. So one thing that I've noticed when helping students out is, although they're in college and have high school backgrounds and have done algebra and should have been comfortable with that stuff, when you put it in a new context like calculus or physics or some college level contexts, a lot of the times they get really, really scared about stuff that they actually have already covered. But I just want to write it out like this to make it very explicit that the calculus part is just for finding the derivative, which is equal to the slope. And after that, you have a slope and a point. All of the rest is 8th grade math. Sound okay?
Yeah.
Okay. So then let's just go ahead and try to figure out what the tangent line is. Sorry, the slope is. So then that's the limit as h goes to 0 of f of, I guess, a plus h minus f of a over h. And that's 3 over a plus h plus 2 minus 3 over, what is it? A plus 2? Over h. Again, every single time I'm supposed to be writing the limit, but I'm just kind of lazy and out of space. Limit of h goes to 0. And at this point, we just cross multiply and try to figure our way through these problems pretty much like we always do. So this turns into 3a plus 2 over a plus h plus 2, a plus 2, minus 3 times a plus h plus 2, a plus 2. All over h, yeah? And at this point, I'm just going to look for cancellation. The 3a cancel out, the 6 cancels out, so all that's left on top is minus 3h, I think, over h times a plus h plus 2, a plus 2. So then the h goes away. Or, sorry, the top and bottom h go away because they cancel out perfectly. But then limit as h goes to 0, well, then this just goes away too. And all that I'm left with is minus 3 over 2a plus 2. I hope. I don't know if that's right. What was a again? Was a 1?
Yeah, a was equal to 1.
A was equal to 1. So plugging that in, what am I getting here? I'm getting a slope of minus 1/2. Did I go wrong? Yeah, I'm getting a different value from what the teacher is getting. And I'd like to quickly sanity check myself. Because it looks like I'm getting minus 3. Oh, wait a minute. 2 times 3. It looks like I'm getting minus 1/2. Okay, let me double check. 2, so then y prime is equal to minus 3 over x plus 2 squared. Minus 3 over 3 times 3. Yeah, I made an arithmetic mistake somewhere. The answer should be minus 1/3. Let me go find it. I'm really stupid. I should have been multiplying these two together. I added them instead of multiplying. So that's my bad. You see what I mean? I just did a very silly mistake. A plus 2 times a plus 2 is a plus 2 squared. And after I caught that, it's pretty straightforward. This should be 3 squared. Sorry, this should be minus 3 over 3 squared, which is equal to minus 1/3. With me so far? So this is the slope right here of your tangent line. Minus 1/3. So at this point, you don't even need to worry about the curve anymore. The problem just reduces to, there's a point 1, 1, and we know that the slope is m is equal to minus 1/3. So this becomes just 8th or 9th grade algebra at this point. I guess for the sake of posterity, I can finish doing it out. But I'm really stressing that this is stuff that you ought to already know. I think I'll just use point slope form, which I believe is like, do I even remember point slope form? No, I don't. I do, but I'll stick to y is equal to mx plus b. So at this point, 1 is equal to m is negative 1/3 times 1 plus b. So I believe b should just be equal to 4/3. And your final answer is just y is equal to minus 1/3 x plus 4/3. Yeah. Does that make sense?
Yeah.
Okay. If anybody is confused, please speak up. Do we have any other problems? Anything else you'd like to ask? If not, I guess I can just go wrap up the other problems in the practice midterm. But yeah, any suggestions at the moment? Okay. I'll try number 5 from the practice midterm. which is a movie theater has a differentiable function t is equal to g as a function of c, which models the number of movie tickets. So this is movie tickets sold, and cost of a single ticket is c. So this is basically a completely qualitative problem, where you might have some curve that looks like, who knows, maybe it looks like this, or maybe it looks like this. But the idea is that it's tickets as a function of cost. Tickets sold as a function of cost. And just from real world logic and economics and supply and demand, you kind of expect that the higher the cost goes, the lower the number of tickets sold goes, right? Because more expensive things, you expect to sell less of fewer of them. That's not so much math as it is just real world intuition, though. But the idea here is that g prime of c just means dg dc, or basically in terms of the word problem, it's the rate of change of number sold with respect to cost. That's what that means. So it's like if you made a small adjustment to the cost of the ticket, the slope would tell you the rate at which the number of tickets you sold changes. Yeah, and that's literally what it means. And when we look at something like the second part is kind of weird, where it's asking, if you have g prime of 10, do you expect it to be positive or negative? And I don't think this is math. I think this is pretty much real world logic. But I guess it's saying that if it's a $10 ticket and you consider increasing the cost by a little bit, right? If you basically consider moving to the right on this curve, it's basically saying that you would expect the number of tickets sold to go down by a little bit. So I would expect this to be negative from real world logic. Now, to be clear, I think the curve looks like this because I've studied a tiny bit of economics where they say that supply demand curves look like it. If it didn't follow real world logic, if the curve looked like this instead, then the derivative would be positive. But honestly, I kind of feel like this is a bad problem because it kind of requires a little bit of, real world economics intuition to answer, at least if I'm understanding the question correctly. Are we all on the same page?
Yeah.
Okie dokie. So I wonder what else there is to say.
Would
what's up?
the units for that problem be tickets per dollar?
Yes, that's right. That's exactly right. Tickets per dollar. And maybe it's worth drawing an analogy to position with respect to time. But so if you have time and you have a position on the x-axis, position with respect to time, right? So you just imagine someone, this is the x-axis and the person is walking along. If x position is in meters and t is in seconds, then x prime of t is basically just saying this is their velocity, which is measured in meters per second. Yeah. So the derivative is basically taking whatever y is and sort of dividing it by x. That's how you find the units. Okay. I guess I'll just keep moving on. But f of x, if they ask you to find the inverse of a function, questions like these are sometimes hard because it's sometimes really, really hard to isolate x. But the point of this problem is, let's rewrite this as y of x. The idea is that given y in terms of x, the inverse is asking you to find x in terms of y. And to do that, we basically just got to group up x and we basically just got to isolate x is what we need to do. So is that equal to e of x? This turns into 3y minus 5y e to the x is equal to e to the x. So 3y is equal to e to the x 1 plus 5y. Yeah, I'm just doing two steps together real quick. And then you just isolate the x So 3y over 1 plus 5y is equal to e to the x. And at this point, you just have to take a natural log to invert it. Does that make sense?
Yes. That
Okay.
makes sense.
Alrighty. Are we getting to the end of the problems? Tan of x, final horizontal asymptotes. Oh, okay. There's another question where they're asking us to find the horizontal and vertical asymptotes. I think one of them we already did, right? So for 7a, I'll just remind it because I think only a couple people were here at the time, but x squared minus x minus 6 over x squared minus 2x minus 3. But this is equal to x plus 2, x minus 3, and x minus 3, x plus 1, I think. So, the x minus 3's cancel out, so you're going to get a point of discontinuity. But that's irrelevant to the question because it's asking about asymptotes, right? So the only asymptotes are going to be when x is equal to minus 1, because that's when it blows up. If there was an x plus 1 on the numerator, it would be a different story. But when x approaches -1, this value becomes very close to positive 1, so a nice finite number. But this value over here becomes absurdly small, which means that the fraction becomes absurdly large. And yeah, so that's why we'd expect a vertical asymptote. As for a horizontal asymptote, we basically just go out to infinity, right? The limit as positive infinity, which just looks like x plus 2 over x plus 1. And that appears to just approach 1. So that's 1. Actually, I'm not going to draw it. I'm just going to say it approaches 1, and I'm not going to say whether from up or down, because it doesn't really matter. But then for negative infinity, you do the exact same process. Negative infinity, x plus 2 over x plus 1. And we see that also, it's basically negative infinity over negative infinity, which just approaches 1 as well. So there's basically a horizontal asymptote at y is equal to 1, and x equal -1 is the vertical asymptote. So just 2. The next one, g of x, is equal to tan of x. Just sine of x over cosine of x, right? And this blows up whenever cosine of x is equal to 0. And that happens whenever x is equal to, I think we said it was some pi over 2, 3 pi over 2, 5 pi over 2, etc., right? So I think this is basically pi over 2 plus k pi for some. Is this right? Yeah, for some k. And if we graph this, I think that's basically saying tangent looks something like this, I believe, where there's a vertical asymptote at each of these. So your answer would probably be there's a vertical asymptote whenever x is equal to this. The reason that I guess there's something I should emphasize a little bit, because I think there was some confusion earlier, but when you have x minus 3 on top and x minus 3 on the bottom, the reason we cancel this out is because together they're basically just have a value of 1, right? Even as you approach 3 and get really, really close, the thing is that x minus 3 and x minus 3 are exactly the same thing, so there's no behavior that, there's no the behavior doesn't blow up. It doesn't go to infinity. There's no asymptote there because they're exactly the same. And they cancel out. So I guess if you wanted to do sine over x over cosine x super thoroughly, you would just have to verify that every time cosine of x is approaching 0, sine of x is not also 0. And we know that's true just because the two functions are sort of like offset by some phase, right? If this is cosine, and this is sine, every time cosine is 0, sine is actually at its maximum. So you know that the top is just some finite number when, the top is just 1 when cosine is very, very close to 0. Or, sorry, I should say that differently. Sine is very, very close to 1 when cosine is very, very close to 0, which is why this blows up. If this was cosine over cosine, it'd be a different story, right? Okay. So I guess we'll just wrap these up and maybe call it a night. Maybe there's some other problems. So this is x over x minus 3 times x plus 1. X minus 3 times x plus 1. So looking at this, there's going to be two asymptotes. One at x is equal to 3, and one at x is equal to -1. And I don't even feel like drawing this entire thing out, to be honest. I'll just look at the limiting horizontal behavior too. But the limit as x goes to positive infinity looks kind of like, if you're doing it carefully, you would divide top and bottom by the leading polynomial. But if you're doing it, maybe a little bit more quickly, you can just kind of see that the behavior is kind of like x over x squared. When I do the tilde, it means like similar to, right? It's kind of hand wavy, but this just becomes 1 over x, which goes to 0. So I would expect one horizontal asymptote to be 0. And as it turns out, the other horizontal asymptote is also 0 for almost exactly the same reason. All right, so when you have x over x squared minus 2x minus 3, this basically becomes x over x squared. And as x goes to negative infinity, this becomes it sort of becomes -0, right? But -0 is also just 0. See what I mean? So for this problem, I would say y is equal to 0 and x is equal to -1 and 3 are going to be our asymptotes. Oh gosh. Yeah, these problems are getting a little bit repetitive, but let's just wrap them up. So the next one is x squared minus x minus 6 over x. So this just looks like x minus 3, x plus 2 over x. And for this one, the bottom is only going to blow up at x is equal to 0, right? So there's going to be a vertical asymptote at x equals 0. And then in terms of the horizontal asymptotes, we have to look at in plus minus infinity as always. But as x goes to infinity, x squared minus x minus 6 over x, it should be pretty clear that this just, becomes sort of like x squared over x, which goes to positive infinity. So I believe we say that that is not an asymptote, but maybe check against your homework problems, because that's ultimately a semantic issue more than it is a math issue. But for a limit as x goes to negative infinity, it should be very similar, right? X squared over x. So, but this time it's negative, so there's a negative infinity that pops out because there's a sign difference. So say that. So I think for this problem, the only asymptote is vertical. X is equal to 0. Any questions on that? Are you all just very quiet?
Yeah.
Yeah. Are you feeling okay? What's up?
Yeah.
Alrighty. Maybe I'll just move on to the last one. This one's kind of interesting. It's the natural log. So this is basically asking, the natural log kind of looks like this, right? So the natural log, remember, the natural log of 0 is does not exist. It's undefined. But just based on the definition of natural log, you can get arbitrarily close, to 0. Sorry, as x gets arbitrarily close to 0, natural log just blows up to negative infinity down there. So I would call that a vertical asymptote. X is equal to 0. But is there a horizontal asymptote for natural log? Which is kind of another way of saying, is there some limit above natural log? Is there some value of natural log that it does not go over? This basically is not so much a problem-solving question, but do you know your natural log function well question. What do you all think? Is there a limit to natural log?
I don't think there would be a horizontal
Yeah,
asymptote
I
for
agree.
natural log.
Natural log grows really slowly, but as it turns out, it grows just fast enough to go off to positive infinity. Right? And the way that you see this is, for any number n, I can find a x such that ln of x is greater than n by just exponentiating both sides, right? That would just become, the task of finding some x larger than e to the n, which is doable because, I can choose anything for my x. Yeah. Natural logs are very important if you ever go further in computer science or, STEM in general. But yeah, I think that covers it, right? Is there anything else?
Would you mind re-explaining how to find the horizontal asymptote? I'm still a little bit confused in general.
The horizontal asymptote just in general?
Yeah.
Yeah, the horizontal asymptote basically asks you to plug in positive and negative infinity, if they're defined for that function, and see what the limiting behavior is. So for this function, it's only positive infinity because natural log is not defined for negative x values. But basically, for horizontal asymptotes, you plug in infinity, and you see if there's anything that the function approaches in the limit. If there's some, how do you put it? If there's some horizontal asymptote, right? Does the function get arbitrarily close to some constant function? That's basically how you determine a natural log. So I think for the last problem was this, where as x goes to infinity, this sort of looks like x over x squared, which just approaches 0. So in the positive direction, it just looks like it becomes really, really close to 0. And similarly, in the negative x direction, you sort of do the limit of x goes to negative infinity. And that behavior is also x over x squared, which also approaches 0. So that's a horizontal asymptote. I think it's basically, if you take the limit as it goes to a positive or negative infinity, and you get a finite number as the limit, I would call that a horizontal asymptote. Does that seem reasonable?
Yeah. Quick question.
Sure.
So for the x over x squared minus 2x minus 3, how did you go from that to x over x squared again?
Yeah, I just kept the limiting behavior. Because as infinite gets very large, x squared dominates the behavior, so 2x minus 3 doesn't really matter. I think the way that they talked about this rigorously was probably dividing everything through by the leading polynomial. So like divide by x squared, divide by x squared, divide by x squared, divide by x squared. And when you put it this way, you can kind of see that 3 over x squared and 2x over x squared go to 0, right?
Yeah.
And all that's left is 1 over x and 1. And this goes to 0.
Okay.
You see that?
Good. Yeah.
Yeah. Like, the slightly more rigorous way to do it is dividing through by the leading term. But, like, at a certain point, you can just eyeball it, right? Like, x, is a dominating term up top. X squared is a dominating term at bottom. With a bit of repetition, it should be clear that this is basically just 1 over x in the limit. See what I mean?
Yeah.
Or rather, maybe negative 1 over x, because it's going to negative infinity in this case. I'm sorry, just pretend I didn't say that, just 1 over x. The negative sign is already captured inside the x. Alrighty. Yeah, I think that covers most of the problems. Oh shoot, I guess we didn't do question 2, which was evaluate each of the following limits. I don't know. You want to do them, or do you all feel like you've had enough?
I think extra practice would be good for us. So.
All right, I'll do these problems and then maybe call it a night. So it's basically saying evaluate the limits, x goes to 2. And by the way, when if your test is on Friday, I advise you to maybe go through and do all of these yourselves. tonight or tomorrow. And then if you get stuck on anything, maybe refer back to the video for an explanation. But, I think I can give good explanations, but at some point you also have to take some of the studying upon yourself. But 5x plus 1, evaluate each of the following limits. Okay, there's really nothing to this one because there's nothing really... As x goes to 2, the bottom goes to 11, right? And there's really nothing blowing up here. So this just becomes kind of like 9 plus 3 over 11, which just becomes 6 over 11. Wasn't too much to that one. Okay, the next one asks you to go as x approaches 2 of x squared minus 6x plus 8. It's x squared minus 4. Okay, so this one we can actually talk a little bit about. You can't just plug it in willy-nilly because that blows up. So you have to look at splitting up the top a little bit to see if there's any cancellation. But this turns into x minus 4 and x minus 2. And this turns into x minus 2 and x plus 2. And lo and behold, there is indeed some cancellation. And all that's left is x minus 4 and x plus 2. And at this point, you can take the limit as it approaches 2 with no problem, right? So then that just turns into 2 minus 4 over 2 plus 2 is equal to negative 2 over 4 is negative 1/2. Okay. All right, next one is saying the limit as x goes to 3 from the right of f of x, which is defined as x squared plus 1 if x is less than 0, 1 if x is between the 0 and 3, and 4x if x is greater than 3. Okay, this basically, I'm looking at this right now, and if we wanted to really graph it, we could basically say it looks like a parabola over here, and it looks like a constant function over here for, between 0 and 3, and then it looks like 4x. So this is 12, right? Above. And it's asking you to find the limit as it approaches 3 from the right, so that's basically just writing down here and seeing what the limit is, so that's just clearly 12. Right? For a problem like this, I wouldn't bother taking out the definition of the limit or anything like that. I would just say, like, as you approach the number 12, what value, what height are you approaching from the right? And it's just 12. All right, part D is limit as x goes to negative 4 from the left. 1 minus 2x over x minus 4. What does this become? So you can't just plug it in because 4 minus 4 blows up. So you gotta think about it, but yeah, what do we actually want to do about this? Okay, it looks to me like there's really no way to simplify this, right? So the top, it basically, if you tried to plug in 4 over here, it looks like this blows up. Sorry, it looks like the bottom blows up, but the top is just 1 minus 2 times 4 is equal to 1 minus 8 is equal to negative 7. Right? So it's clear that there's a vertical asymptote at x is equal to 4. Right now, it's just a question of whether it approaches positive infinity or negative infinity. And to figure that out, I think we just need to look at the signs. So if it's approaching 4 from the left, you can almost imagine like x is equal to 3.9, or maybe 3.99, and just ask yourself whether the denominator is positive and the numerator is... Sorry, you could ask yourself just the sign of the denominator and the sign of the numerator. So if it's just a little bit less than 4, the denominator is going to be negative. And if it's, if it's a little bit less than 4, well, that's still just something very close to negative 7, right? So it's both of these are going to be negative, so it's going to cancel out, and it's going to approach positive infinity. That's going to be your limit. Does that make sense?
Yeah.
Okay. And I think for the very last one for this night is the limit as x goes to 0 from the right. Oh gosh, an inverse tan. What do these look like? That's really nasty. So what this is saying is, first we need to remind ourselves what an inverse tan looks like. And I think it's basically just that, right? It goes between pi over 2 and pi over 2. And I guess that's just something you need to know off the top of your head. Reminder that a regular tangent looks kind of like this, where there's sort of an infinite number of them with vertical asymptotes, and the inverse tan is just taking the principal one, the one in the middle, and just kind of flipping y and x to look like this. But the idea here is, okay, so this is what tan -1 looks like with regards to x. But right now it's asking us what tan -1 of 1 over x is as x approaches 0 from the right. So break this down into 2 layers. What is the limit as x approaches 0 from the right of just 1 over x? And that's... Sorry, maybe I should just drag this down a little bit to do this problem in steps. But to remind you, 1 over x basically looks like this, right? And as it approaches 0 from the right, this is just positive infinity. So this limit is positive infinity. X is going towards... 1 over x is going towards positive infinity. So at this point, the question is basically saying that this thing on the inside is going towards positive infinity. What is arctan or tan -1 going towards? So, you know what? Maybe I should call this y instead. I'm renaming it, right? So let y be defined as 1 over x, and they're both going towards positive infinity. So then 1 over x, the limit as x goes to 0 is the same thing as limit as y goes to infinity. Limit of y. You see what I did there? I just replaced x with its reciprocal, y, to make this a little bit more clear. But at this point, it's just asking what the behavior is when y goes to infinity or when x goes to 0 from the right. And that's just going to be positive pi over 2. That's your answer. I feel like I might have been a little bit choppy in this last explanation, but does it make sense, or do you feel like I've gone too fast? What's the feeling here?
I think it makes sense.
Okay. Alrighty then. Good. Yeah, unfortunately, this last problem basically boils down to how comfortable you are with tangent, or arctan. And this is just what that function looks like, and I think you just got to know it. But I do think it's a little bit informative about doing one limit that's 1 over x as x goes to 0, because that's exactly the same thing as just 1 over x going to infinity, right? And if it confuses you to think about the limit of 1 over x as it goes to 0, you can just rewrite that as the limit of y as y goes to infinity. And if this problem was, for example, limit as x goes to 0 from the left of 1 over x, then in that case, y would have had to go to negative infinity. Does that make sense? Because 1 over x is this function right here. And if x was approaching 0 from the left, then this function is blowing up towards negative infinity, which is the justification for y going to negative infinity. Okay. Gosh, I hope that's not too much. Any other questions? We've gone through basically the entire practice midterm at this point, as well as a couple of extra problems. And, it was recorded, so I'll put that on YouTube and link to it so that anyone can refer back. But I hope that helps with your exam. And, you can always just ping me if you have questions. I try to help out when I have the time. Anything else? Alrighty, I guess.